Section 1.1.8 Cap and Cloud Systems. What gets sacrificed and why? At some point, almost everyone who works with cloud systems runs into the same confusion. A system suddenly stops responding, or it keeps responding, but the data doesn't look quite right. Or everything works fine, until two parts of the system can't talk to each other anymore. At first glance, these problems seem unrelated, but they all have the same root cause. When this happens, people usually ask the same question: why is the system behaving like this? This is exactly where the CAP theorem helps. CAP isn't a slogan, and it's not something you learn just to sound smart. It's a way of understanding what systems are forced to do when reality interferes. At its core, CAP answers one very practical question. When the network breaks, what is the system willing to give up? Before we go further, let's slow down and set the context. CAP applies to distributed systems. That simply means systems made of multiple machines working together. Those machines might live in different data centers. They might even be on different continents. And here's the important part. Those machines depend on networks to stay in sync. Most of the time, that communication works. But sometimes it doesn't. And when it doesn't, systems are forced to make choices. That's what CAP is really about. CAP describes three properties. Two of them represent what we want from a system. One of them represents a reality we cannot avoid. The first property is consistency. Consistency means that everyone sees the same data at the same time. If something changes, all users should immediately see that change. Think about a bank balance. If money moves, you expect the new number to appear right away, everywhere. The second property is availability. Availability means the system responds when you ask it something. Even if parts of it are under stress, it still answers instead of freezing or timing out. The third property is partition tolerance. Partition tolerance means the system continues operating even when parts of it can't communicate. This can happen because of network issues, data center outages, or temporary region isolation. These situations are called partitions. And in large cloud systems, partitions are not rare accidents. They are expected. Now we can state the core idea behind CAP. When a partition happens, a distributed system cannot guarantee both consistency and availability at the same time. It has to choose. This choice doesn't matter much when everything is healthy. In normal operation, systems often provide both. But under failure, a decision becomes unavoidable. And that decision defines how the system behaves in the real world. Let's make this concrete. Imagine the same database running in two locations. As long as the connection between them works, everything stays in sync. Now imagine that connection breaks. At that moment, the system faces a decision. One option is to stop accepting changes until communication is restored. The data remains correct, but users experience downtime. The other option is to keep responding and accept changes, even if the data isn't perfectly synchronized yet. The system stays alive, but some users may briefly see outdated information. Both options are reasonable, but the system can't do both at once. That's CAP. This is also where many interview questions quietly come from, even if they never mention CAP by name. If you're asked about it, you don't need formal definitions. What matters is showing that you understand the trade-off. A natural way to explain is this. When parts of a distributed system can't communicate, the system either pauses to protect correctness or keeps running and fixes inconsistencies later. Different technologies make different choices based on what they are designed to optimize. That kind of explanation signals real understanding. Now let's look at how real cloud technologies make these choices. Some systems clearly prioritize correctness. PostgreSQL is a good example. When its primary node can't safely coordinate with replicas, it protects data integrity first. It may pause or refuse writes until everything is back in sync. In CAP terms, it chooses consistency and partition tolerance, and gives up availability during the problem. This makes sense when wrong data would be unacceptable. For example, in banking systems, healthcare records, or transactional order processing. In managed cloud services like Amazon RDS for PostgreSQL, this behavior is enforced through synchronous replication. If a replica goes down, writes stop until recovery completes. Other systems make the opposite choice. DynamoDB is designed to stay available. When a partition happens, it keeps accepting requests and resolves inconsistencies later. This is known as eventual consistency. Users might briefly see outdated data, but the system corrects itself automatically. In CAP terms, DynamoDB prioritizes availability and partition tolerance while sacrificing immediate consistency. This works well when applications must not freeze. Social feeds, shopping carts, and recommendation systems are common examples. That's why large platforms like Netflix, Airbnb, and Uber rely on this model. In global setups, DynamoDB uses asynchronous replication across regions, clearly signaling that availability comes first. Kafka follows a similar philosophy. When brokers lose connectivity, Kafka continues accepting data. Once communication is restored, messages are processed and nothing is lost. This makes Kafka a natural choice for event streams, telemetry, and real-time pipelines, where stopping the system would be worse than delaying perfect consistency. Some guarantees, such as strict ordering, depend on configuration, but the system stays alive. MongoDB sits somewhere in between. Depending on configuration, it can behave more like a consistency-first system or more like an availability-first one. That flexibility is powerful, but it also means engineers must be careful. Misconfiguration can easily lead to unexpected behavior. And this brings us to an important takeaway. CAP isn't about good or bad systems. It's about choosing what matters most when things go wrong. Engineers don't use CAP to win arguments or pass exams. They use it to design systems. They ask simple but important questions. If the network splits, should the system keep responding, even if data becomes temporarily inconsistent? Or should it pause to avoid returning incorrect results? What matters more to the business, accuracy or uptime? Real systems often mix approaches. A consistency-first database might store user accounts. An availability-first system might handle notifications or analytics. Teams even test these decisions intentionally, using techniques like chaos engineering. Tools such as Netflix's Chaos Monkey simulate failures to observe system behavior. Here's an easy way to remember CAP. Some systems protect correctness first. Others protect availability first. There is no perfect choice, because failures are unavoidable. Each approach exists because different problems require different guarantees. That's engineering. Now that we've seen how systems behave under failure, we can move to another force that shapes cloud architecture just as strongly: money. Because in the cloud, technical decisions are also economic decisions. Next, we'll talk about cloud economics, operational expenditure versus capital expenditure, and why this matters for system design. End of section 1.1.8.